Well, welcome. Let's look at section 4.1. And section 4.1 is all about systems of linear equations. And you can see we're going to do this in two parts today. We're going to do day one, and then tomorrow we'll work on day two objectives. So today we're going to decide whether an ordered pair is a solution for the linear pair. We're going to solve it by graphing. And also, we'll talk about a substitution method today. So let's get started. What's the idea behind a systems of equations? Well, this example that you're looking at is all about camera sales. And there used to be conventional cameras with film, and then digital cameras came into the market. And our graph looks like it's sales in millions of units in the years since 2000. So we'd have 2000, 2001, 2002, 2003, so on. And you can see very clearly that digital cameras increased in sales as the years passed by, and eventually overtaking conventional cameras. There is a point, and I'm spotting it on the screen, where they actually had equal sales. And it looks like that happened at, I don't know, 3.5, 3.6. So maybe, 2003, June, July, somewhere in that time frame, the sales were actually equal. A set of equations is called a systems of equations. And that means that we're just working with more than one equation. We got a system going. Example 1, decide whether an ordered pair is a solution. And they've given us two possibilities, 4, 2, and 3, -12. In order to find out if it's a solution, we're going to substitute those values in. We know in an ordered pair that the ordered pair comes in X, Y configuration. So for X, I'm going to plug in 4. That's going to give me 2 times 4 plus Y is 2 equals -5. Now, let's see if that is true. So I'm going to have 8 plus 2 equals -5, or 10 equals -5. That is not true. So that is not a solution. And I could check it into the second equation and see if it works, but I already know since I plugged it into equation 1 and it didn't work, it's not a solution to both equations at the same time. So this one, I'm going to say no. For part B, the solution 3, -12, let's give it a go. Let's see if it works. So we're going to test, I'm going to go into equation 1, and I'm going to go 2 times 3 plus a -12 for y equals -5. That means I have 6 minus 12 equals -5. Well, we're close, but not quite there. This is also not a solution. So, both of them were not solutions to our system. But let's look at how you could determine what is a solution. So example 2, we have the two systems, equation 1, equation 2, and we're solving this one by graphing it. And we know how to graph linear equations. We could have put this over into y equals, I'm going to subtract 2x, mx plus b mode, and I start graphing at -5. And then I've got a slope of up to left 1 so that I get that negative slope. So this looks like the equation corresponding to that line. And then I would assume that this must be that particular line. And where they intersect, right here, is the solution that fits both equations. So let's label what that solution looks like. In x terms, it's -3, and the y value would be 1. So I have the ordered pair. -3, 1 is the solution. Let's verify it. Let's take 2 times -3 plus 1 equals -5. I'm testing it out in equation 1. That's going to give me -6 plus 1 equals -5. -5 equals -5. Yes, that checks out, doesn't it? So it is a solution to equation 1. That doesn't necessarily prove that it's an equation to a solution to equation 2. So let's check it in equation 2. So it's got the opposite of x, so the opposite of -3 plus 3 times 1 equals 6. Lost my spot there. And that's going to give us a plus 3, isn't it? So it's going to say 3 plus 3 equals 6. Oh, indeed. 6 is indeed equal to 6. That solution, -3, 1, fits both equations. We proved it algebraically as well. You just have to be really careful when you graph these that you're graphing accurately. And that's why I always do a substitution into the actual equations to make sure it works. All right, example 3 is all about, I'm trying to see where example 3 is. It's on your next page. I think I might have my screens out of order. Or I'm missing a screen, aren't I? There's the screen we're looking for. Sorry about that. Possible solutions when solving a system of 2 equations. There's some words for these, and let me see. Once that gets parked, I can't move the picture. Alrighty, so the words that we're talking about here is called a consistent, independent systems of equations when there is one solution. So this is going to be one solution to our system. The word consistent means there is a solution. And the word independent means that there is one point in common. They're independent of each other except for where they cross. So let's draw ourselves a picture. We have one equation. And where should we draw our second one? We have the second equation. And they just happen to meet right there. And that is their consistent, independent systems of equations with one solution. A consistent dependent, well, we know what consistent means. It means it has a solution. Dependent, they share the same line. So what that looks like is I have equation 1 here in red, and equation 2 happens to land right on top of it identically. And so they would have oodles of solutions. All the points, trying to draw a bunch of points, on that line are shared solutions. So in this sense, these have infinite solutions. They would be the xy pairs that fit the line. Okay, the last one is called inconsistent. Inconsistent means there is no solution. When would that happen? When would it be the case that two lines do not intersect? Oh, you know what that is, don't you? That would be where I have two parallel lines. So we have parallel lines in this scenario. And they will never intersect. All right, let's go on to that example 3 that I was getting to come up on the screen earlier, and that will finish our work for the day. The rest of it will hit tomorrow. So the substitution method can be used when one equation is solved for a variable. So that's kind of how we get it started. When you solve one equation for a variable. So if I'm working in x and y's, maybe I'll get it solved for x. So it'll say x equals. Or perhaps I can see that it would be easier and I might choose to solve it for y. So let's look at our equations 1 and 2. They're numbered for us. Which one do you think would be easy to use as our substitutor? Well, I'm looking at equation 2 because it's already solved. Wow, that's a gift. So this is already solved for x. Let's use that. So I'm going to take equation 2 and sub it into equation 1. Now, it's not always going to be equation 2 that subs into equation 1, just for this particular example. Take equation 2, sub into equation 1. All right, let's give it a shot. I'm going to take equation 2, and x represents 2 minus y, so that's going to substitute in for 5x minus 3y equals negative 6. So this is going to look like 5. Substitute x is 2 minus y, and then minus 3y equals negative 6. Now you'll notice our equation is all in numbers and y's, so we can solve for y. So let's simplify. Bring like stuff together. So that's going to give me 10 minus 5y using distributive property minus 3y equals negative 6. Keep simplifying. 10 minus 8y equals negative 6. I'm going to leave the 8y here, and I'm going to subtract 10 from both sides, giving me negative 8y equals negative 16. And finally, using division, we're going to get our solution for y. It looks like y is equal to 2. That's looking like a z. Okay. There's half of our solution, right? Because we need an ordered pair. So we're going to find x. And we know that y equals 2. So using either equation 1 or 2, I like 2, I'm going to use equation 2, and I'm going to have x equals 2 minus y is what equation 2 is. So I'm going to have x equals 2 minus, let's substitute y with that 2 that it's equal to, and get our solution that x equals 0. 0 is a number, so we have come upon our solution set. It is the ordered pair 0, 2. Okay? And that is, I'm sure you've done some substitution methods before. That is finding an ordered solution using substitution. Now, I didn't see equation or example 4. I guess we had one more to go. This one's a little harder, and I'm glad we have it because the last one was kind of set up for us. So now I'm going to look, which variable do I want to solve for and using which equation? Well, I'm really in love with equation 1 because it simply has a single y in it, and I can solve for that very easily. So let's solve equation 1 for y. Solve for y, equation 1. All right, so I'm going to start out with 4x plus y equals 5. Simply subtract 4x over. You might have been able to see that in your head. The answer is going to be negative 4x plus 5. All right, so we have a y equals. Perfect. Now let's substitute into the other equations. Because it's a system, we have to get both equations involved in the process. So sub into equation 2. And I'm going to take equation 2, which says 2x minus 3. And instead of y, we're going to put in negative 4x plus 5. You know, if you use color on your notes, you might find that it's easier to read them when you're looking back and seeing what you did. It just, accentuates some things for us. All right, now we're going to do distributive, so we're into a simplify step. Find what works for you when you're taking notes. 2x plus 12x minus 15 equals 13. Keep simplifying. 14x minus 15 equals 13. Looks like we need to add 15 to both sides so that we can get x isolated by itself. Final step, we're going to divide by 14. And turns out that our x value is 2. I'm going to fit this in. We're going to make sure, we're going to, get that out of the way for a moment. What I'm trying to do is not working out. There it did. Okay, because now I can make that a little smaller. And I will have room for. What happened to my other equation? Oh, there they are. Woo! All right, so final step. Let's go after finding y. We know x, right? We know x is 2. Now we need to find y. You can use equation 1 or equation 2, or we can grab the equation 1 that's already solved for y. So I know that y equals negative 4x plus 5. Let's substitute in our 2. And it looks like we get negative 8 plus 5 equals negative 3. So y equals negative 3. And we throw this together to give the ordered pair. Our solution is, I lost track, 2, negative 3. Fantastic. Have fun with these. I never mind doing systems of equations. I think they're rather nice. I'm not sure what's up with the blocks here, guys, but I'm going to move those for you. So the ordered, or the homework for the day is found on page 17, and you're doing 7 through 19, 71, and 72. Please show your work. It looks like which ones could be ordered pairs, so you're just going to try and label what you think that point is. Look for that intersection. That's the graphing method. Match each system with its correct graph. You should be okay with finding linear functions and their representative graph. And decide whether the ordered pair is a solution. So this, try it into each one of them, not just one of them. If it doesn't work on the first one, then obviously the answer is no. But otherwise, if it does work in the first equation, you also have to try it in the second, make sure it works in both at the same time. And then I think your final questions are where you actually get to solve them. 3 of them by graphing, 3 of them by substitution method. So you may want some graph paper. I will put that in Schoology for you. So if you want to print your own graph paper, you certainly can, or if you have some at home, use that. And then 71 and 72 aren't too bad, just little quick questions there. All right, have a wonderful day. Bye-bye.